Exothermic welding, also known as CAD welding, is a common practice for grounding applications, particularly in high current systems. It involves creating a permanent low-resistance connection between two metal conductors using a highly exothermic or heat-producing chemical reaction. In modern electrical installations, comprehensive grounding is essential for safety and proper equipment operation. The National Electrical Code, or NEC, and other industry standards require multiple grounding connections to ensure redundancy and minimize the risk of electrical shocks or fires. Ground bus bars are used to consolidate multiple grounding connections into a single point. Depending on the size and complexity of the electrical system, a single bus bar may need to accommodate multiple conductors, each of which must be properly connected. For large installations, 4-inch by 12-inch bus bars may be necessary to accommodate numerous grounding wires. To fit multiple grounds onto a single bus bar, it is common practice to lay out the wires long and then fold them back up. This allows for the connections to be properly secured and ensures that each conductor has a good electrical connection to the bus bar. The requirement to connect building steel and gas pipe to the grounding system may vary depending on local codes and regulations. However, it is becoming more common to require all conductive materials within the facility to be connected to the grounding system for safety and potential equalization purposes. The extensive grounding requirements and the use of exothermic welding for grounding bus bars are common practices in today's electrical installations. They provide a reliable and safe means of ensuring proper grounding and minimizing the risk of electrical hazards. When performing exothermic welding, safety is paramount. Always wear appropriate personal protective equipment, including eye protection, gloves, and flame-resistant clothing. Ensure that the work area is clear of any flammable materials. Follow the manufacturer's instructions for the specific exothermic welding kit being used. Proper preparation is essential for a successful exothermic weld. Clean the surfaces of the conductors to be joints to remove any dirt, grease, or oxidation. Use a wire brush or abrasive pad to ensure a clean, bright metal surface. Securely clamp the conductors in place to prevent movement during the welding process. Follow the manufacturer's instructions for the correct mold size and filler metal for the conductors being joined. Overfilling or underfilling the mold can result in a poor quality weld. After the exothermic reaction is complete, allow the weld to cool completely before removing the mold. Inspect the weld for any defects, such as porosity or cracks. If any defects are found, the weld should be repeated. Grounding systems are designed to provide a low impedance path for fault current to return to the source. This helps to ensure that overcurrent protection devices, such as circuit breakers and fuses, will operate quickly and effectively to clear the fault. A properly grounded system also helps to minimize the risk of electrical shock by providing a low resistance path for current to flow back to the source in the event of a ground fault. The NEC specifies the requirements for grounding and bonding electrical systems. Article 250.4 covers the general requirements for grounding and bonding. This section outlines the requirements for grounding electrodes, grounding conductors, and bonding conductors. It also specifies the methods for connecting grounding and bonding conductors to equipment and structures. The grounding electrode system should consist of one or more grounding electrodes that are bonded together to form a single grounding system. Common grounding electrodes include metal underground water pipes, metal building frames, concrete encased electrodes, and ground rings. The grounding electrode conductor connects the grounding electrode to the equipment grounding bus in the service equipment. The size of the grounding electrode conductor is determined by NEC Table 250.66 based on the size of the service entrance conductors. Bonding is the process of connecting all metal parts of an electrical system together to create a low impedance path for fault current. Bonding conductors are used to connect metal enclosures, raceways, and other metal parts to the equipment grounding bus. The size of the bonding conductors is determined by NEC Table 250.102 based on the size of the circuit conductors. The equipment grounding conductor provides a path for fault current to return to the source. It is connected to the equipment grounding bus in the service equipment and runs with the circuit conductors to each piece of equipment. The size of the equipment grounding conductor is determined by NEC Table 250.122 based on the size of the overcurrent protection device protecting the circuit. In addition to the general grounding requirements, there are also specific requirements for grounding certain types of equipment and systems. For example, NEC Section 250.118 covers the grounding requirements for motor vehicles. This section requires that all metal parts of the vehicle that are likely to become energized be bonded to the vehicle's frame. NEC Section 250.166 covers the grounding requirements for separately derived systems such as generators and transformers. This section requires that the neutral point of the separately derived system be grounded to a grounding electrode. Grounding is a critical aspect of electrical safety and should be performed by qualified personnel. It is important to follow the NEC and other applicable standards to ensure that the grounding system is installed correctly and provides adequate protection against electrical shock and fire hazards. Regular inspection and testing of the grounding system are also essential to ensure its continued effectiveness. This includes visual inspection of grounding connections and testing of ground resistance. Any deficiencies should be corrected promptly to maintain the integrity of the grounding system. The use of exothermic welds is often preferred for grounding connections because they provide a permanent, low-resistance connection that is resistant to corrosion. Exothermic welds are also capable of carrying high fault currents without melting or deteriorating. However, exothermic welding requires specialized equipment and training, and it should only be performed by qualified personnel. In addition to exothermic welding, other methods of making grounding connections include mechanical connectors and compression connectors. These connectors should be listed and labeled for grounding applications and should be installed according to the manufacturer's instructions. The ground bus bar should be sized to accommodate all of the grounding conductors that will be connected to it. The bus bar should be made of copper or another conductive material and should be securely mounted to a non-conductive surface. The ground bus bar should be located in a readily accessible location and should be clearly labeled. When connecting grounding conductors to the ground bus bar, it is important to ensure that the connections are clean and tight. The conductors should be stripped to the proper length and the connections should be made using appropriate hardware. The connections should be torqued to the manufacturer's specifications to ensure a reliable connection. Building steel and gas pipes are often used as grounding electrodes because they provide a large surface area in contact with the earth. However, it is important to ensure that these electrodes are properly bonded to the grounding system. Building steel should be bonded to the grounding system at multiple points to ensure a low impedance path for fault current. Gas pipes should be bonded to the grounding system near the point where they enter the building. The bonding connections should be made using exothermic welds or other approved methods. In some cases, it may be necessary to install additional grounding electrodes to supplement the building steel and gas pipes. This is particularly important in areas with high soil resistivity or where the building steel and gas pipes are not adequately grounded. Additional grounding electrodes can be installed in the form of ground rods, ground plates, or ground rings. The selection of the appropriate grounding electrode depends on the specific site conditions and the requirements of the electrical system. Regular maintenance of the grounding system is essential to ensure its continued effectiveness. This includes visual inspection of grounding connections, testing of ground resistance, and cleaning of ground bus bars. Any deficiencies should be corrected promptly to maintain the integrity of the grounding system. Grounding is a complex and critical aspect of electrical safety. It is important to understand the principles of grounding and the requirements of the NEC to ensure that the electrical system is properly grounded and provides adequate protection against electrical shock and fire hazards. Consulting with a qualified electrical engineer or electrician is recommended when designing or installing a grounding system. They can assess the specific site conditions and the requirements of the electrical system and recommend the appropriate grounding methods and equipment. Proper grounding is not only essential for safety but also for the proper operation of electrical equipment. A properly grounded system helps to minimize electrical noise and interference, which can improve the performance of sensitive electronic equipment. Grounding also helps to prevent voltage transients, which can damage electrical equipment. In addition to the NEC, other standards and guidelines may apply to grounding systems depending on the specific application. For example, the Institute of Electrical and Electronics Engineers, or IEE, publishes standards for grounding sensitive electronic equipment. These standards provide guidance on how to design and install grounding systems that minimize electrical noise and interference. The Telecommunications Industry Association, or TIA, publishes standards for grounding telecommunications equipment. These standards provide guidance on how to design and install grounding systems that protect telecommunications equipment from damage caused by lightning and other electrical surges. Grounding is an essential part of any electrical system and should be given careful consideration during the design and installation process. A properly grounded system provides a safe and reliable electrical supply for all types of equipment and protects against electrical shock and fire hazards. Furthermore, in certain facilities like hospitals or data centers, maintaining a robust and reliable grounding system is not just about safety, it's also crucial for operational continuity. Sensitive medical equipment or critical data infrastructure can be severely affected by grounding issues, leading to inaccurate readings, equipment malfunction, or even data loss. Therefore, a well-designed and meticulously maintained grounding system is paramount in these environments. This might involve more frequent inspections, more stringent testing protocols, and the use of advanced grounding techniques to ensure that the grounding system is functioning optimally at all times. Also, consider that soil conditions can change over time due to factors like moisture content, temperature variations, and chemical contamination. These changes can affect the resistance of the grounding electrode and compromise the effectiveness of the grounding system. Therefore, it's important to periodically test the ground resistance and make adjustments as needed to maintain the grounding system's performance. One effective strategy is to use multiple grounding electrodes connected in parallel. This reduces the overall ground resistance and provides a more robust grounding system that is less susceptible to changes in soil conditions. Additionally, the use of chemical grounding electrodes, which contain chemicals that improve the conductivity of the soil around the electrode, can be beneficial in areas with poor soil conditions. The chemicals help to lower the ground resistance and improve the effectiveness of the grounding system. Remember that a grounding system is not a static entity. It needs to be regularly inspected, tested, and maintained to ensure that it continues to provide the necessary level of protection. Ignoring the grounding system can have serious consequences, including electrical shocks, fires, and equipment damage. It is also worth noting that different types of equipment may have different grounding requirements. For example, sensitive electronic equipment may require a dedicated grounding conductor to minimize electrical noise and interference. In these cases, it's important to follow the manufacturer's instructions and consult with a qualified electrical engineer or electrician to ensure that the equipment is properly grounded. Finally, make sure all grounding connections are accessible for inspection and maintenance. Buried connections are difficult to inspect and repair, and they can be a source of problems if they corrode or become loose. Whenever possible, grounding connections should be made above ground and protected from the elements. Use weatherproof enclosures and connectors to prevent corrosion and ensure that the connections remain tight. By following these guidelines, you can ensure that your grounding system is properly designed, installed, and maintained, and that it provides a safe and reliable electrical supply for all of your equipment. Remember to always prioritize safety when working with electricity and to consult with qualified professionals when needed. They can help you to identify potential hazards and to implement appropriate safety measures. Also, while the NEC provides a comprehensive set of requirements for grounding electrical systems, it's important to remember that local codes and regulations may also apply. Be sure to check with your local building department to determine if there are any additional requirements that you need to comply with. The NEC is updated every 3 years, so it's important to stay current with the latest edition. The changes in the NEC can affect the design and installation of grounding systems, so it's important to be aware of these changes and to comply with them. In addition to the NEC, there are other industry standards and guidelines that can provide valuable information about grounding electrical systems. These standards and guidelines can help you to design and install a grounding system that meets the specific needs of your application. For example, the IEE publishes standards for grounding sensitive electronic equipment, and the TIA publishes standards for grounding telecommunications equipment. These standards can provide guidance on how to design and install grounding systems that minimize electrical noise and interference and protect equipment from damage caused by lightning and other electrical surges. Ultimately, the goal of grounding is to provide a safe and reliable electrical system that protects people and property from electrical hazards. By following the guidelines and requirements outlined in the NEC and other industry standards, you can ensure that your grounding system meets this goal. Always remember that electricity can be dangerous, and it's important to take all necessary precautions to prevent electrical shocks and fires. Consulting with qualified professionals is always recommended when working with electricity, and they can help you to identify potential hazards and to implement appropriate safety measures. Furthermore, it is crucial to understand that grounding is not the same as bonding, although the terms are often used interchangeably. Grounding refers to connecting a circuit or equipment to the earth, while bonding refers to connecting two or more metal parts together to create a low impedance path for fault current. Both grounding and bonding are essential for electrical safety, but they serve different purposes. Grounding provides a path for fault current to return to the source, while bonding ensures that all metal parts of an electrical system are at the same potential, minimizing the risk of electrical shock. When designing and installing a grounding system, it's important to consider the specific characteristics of the site, including the soil resistivity, the presence of underground utilities, and the proximity to other structures. These factors can affect the performance of the grounding system, and it's important to take them into account when selecting the appropriate grounding methods and equipment. For example, in areas with high soil resistivity, it may be necessary to install multiple grounding electrodes or to use chemical grounding electrodes to achieve the desired ground resistance. In areas with underground utilities, it's important to locate the utilities before installing grounding electrodes to avoid damaging them. And in areas with nearby structures, it's important to consider the potential for stray currents to flow through the grounding system. Stray currents can cause corrosion and can interfere with the operation of sensitive electronic equipment. It is important to mention that a lightning protection system is a separate system from the electrical grounding system, although they are often interconnected. A lightning protection system is designed to protect structures from damage caused by lightning strikes, while the electrical grounding system is designed to protect people and equipment from electrical shock and fire hazards. The lightning protection system consists of air terminals, down conductors, and a grounding system. The air terminals are installed on the roof of the structure to intercept lightning strikes. The down conductors carry the lightning current to the ground, and the grounding system dissipates the lightning current into the earth. While the lightning protection system and the electrical grounding system are separate systems, they should be interconnected to ensure that all metal parts of the structure are at the same potential during a lightning strike. This helps to minimize the risk of side flashes, which can cause damage to equipment and injury to people. The interconnection between the lightning protection system and the electrical grounding system should be made in accordance with the requirements of the NEC and other applicable standards. This interconnection is typically made at the service entrance, where the grounding electrode conductor from the electrical grounding system is connected to the grounding electrode of the lightning protection system. The connection should be made using a listed and labeled connector and should be protected from corrosion. In conclusion, grounding is a multifaceted and essential aspect of electrical safety and system performance. From exothermic welding techniques to NEC compliance, every detail plays a role in creating a safe and reliable electrical environment. Whether it's a high school, a hospital, or a data center, a well-designed, installed, and maintained grounding system is critical for protecting people, equipment, and data. Always consult with qualified professionals, stay updated with the latest codes and standards, and prioritize safety in all electrical work. This includes knowing what voltages are dangerous and how far to stay away.